Right, afternoon everyone. Some of you may remember from this morning my background is as an optician, an ophthalmic optician or optometrist. So I have an interest in eyes in my work. I see lots of them every day and in quite a lot of detail. Now, during optometry studies, degree studies at university, you're obviously going to cover the anatomy, that's the structure of the eye and its function as well, and that of also the nervous and visual systems which are involved in our eyesight. And I was struck when studying these things at university by the sheer complexity of these things, the marvel of them, the eye and the visual system. In the past, most people, I'm sure, thought that these things were the work of a creator, a god, but many today attribute them instead to chance events, chance happenings. And this lecture then asks the question, could the eye have evolved purely by chance, or does it present evidence of design? And perhaps a little bit different from many talks you'll hear here in this room on a Sunday afternoon. It's going to be more like a science lesson or a university lecture in tone. And I wrote this talk not necessarily assuming that all my audience would already be convinced of what they thought about this. So, there are scripture references, but they'll follow at the end. Right, so an outline of what we're going to talk about. First of all, we'll talk about the structure of the eye and the way it works, or the ocular anatomy and physiology. And we'll have a brief tour of all that. Then we'll go on to discuss the way in which some biologists think that the eye could possibly have evolved. Next, we'll describe some of the arguments that, instead of that, the eye actually presents evidence of a designer, and we'll visit briefly one or two aspects, one or two topics like embryology, the way the eye develops in an unborn child. And then we'll ask the question, is it possible that the eye, instead of helping us prove that there is a designer, might instead demonstrate some features of poor design, so to speak? When believers in God, or creationists who believe that in a divine creation, when we talk about the eye's intelligent beginnings, this is one of the criticisms levelled at those assertions by some evolutionists. They would ask, how can the eye have been designed by God when they claim it actually shows some evidence of bad design, or something that could not possibly have been designed and intended to be that way? Right, so moving on swiftly then, the first section, ocular anatomy and physiology, the structure and function of the eye. And this is going to be a very brief and incomplete tour. So this slide shows what you might already be familiar with, that the eye is a bit like a camera, or perhaps we should say the camera works a bit like the eye does. A camera has a lens or a series of lenses here at the front which work to focus light from a distant object over here onto a light sensitive film, or in most modern cameras a digital light sensor. And in the same way, this picture at the bottom shows a cross section of your eyeball, and the eye also has a pair of lenses at the front which work to focus light from a distant object onto the retina. That's the light sensitive nervous layer at the back of the eyeball. Okay, a camera also has an aperture at the front which can vary in size in order to admit different amounts of light, and in the same way your eye has the pupil, the aperture at the centre of the coloured part of your eye, which admits different amounts of light and thus regulates the quality of the image as well. So let's see how interactive our audience are today. Here's an illustration of an eyeball, or a globe. You can see there are various structures here. I may or may not have already said what this structure is called at the front, the clear window at the front of the eye. Anyone want to tell me what that is? Anyone remember? So Debbie's going to be providing most of our answers today, I think. So the front of the front of the eye there, that clear window which vaults over the front, is called the cornea. That's a lens. It has most of the focusing power of the eye, 2/3 of the strength of the eye in order to focus images. Behind that, there's a clear fluid. Anyone know what that's called? from their science lessons at school? Nearly. It's the aqueous fluid, or the aqueous humour, yeah. Okay. And then behind that there's the coloured part of your eye, the iris, okay. We've already said that has the pupil at its centre. It controls the size of the pupil. And then behind that there's a second lens, the crystalline lens. Again, this works to focus the image. And when a person develops cataract, it's that part of the eye that becomes cloudy. That's the lens that becomes cloudy. Okay. Now that lens can actually change shape in a younger person. So up until middle age or a bit later, the lens can change shape in order to focus the eye for different distances without the help of needing several pairs of glasses. Okay. And in order to do that, that crystalline lens is attached by little fibres that you can't really see on this picture. It's attached by little fibres to this structure here, which is called the ciliary muscle, and that's a ring of muscle which can change shape in order to either put tension on or relax these fibres which suspend the lens. Now normally when the eye is relaxed, the ciliary muscle is relaxed, the lens is held in tension and it's as flat as can be in order to focus the eye for distance vision, for far sight. And when that ring of muscle, like a sphincter, contracts, the fibres are relaxed, the lens is naturally elastic, it assumes a fatter shape, more curved shape, and that focuses the eye for a nearer object until a person reaches middle age at least. Behind that we have another substance, the vitreous humour, vitreous gel, a clear gel which gives the eye some of its elastic properties, gives it its shape. We'll talk about the vitreous a bit later on. And at the back of the eye you have the retina, the light sensitive neural layer that we've already discussed. And then there's this thing, the optic nerve. This is where all the nerve fibres take the picture information off towards your brain, allowing you to see. How many of you have seen a picture of that kind before? One or two, yeah. You may have seen one last time you visited your own optician. You may have seen a picture like that of your own eye, possibly. Or if you're diabetic, you may have regular diabetic retinopathy screenings where they photograph your retina in order to look for signs of diabetic eye disease, which is very important. It's an indicator of what other diabetic disease or damage might be happening in other structures in your body, like your kidneys, as a result of diabetes and other vascular disease. Anyway, this picture shows the central 45 degrees of someone's right retina, just a small area at the back of the eye. The retina contains a truly vast network of nerve cells, including some which are responsive to light. Anyone know what they are called? Two different sorts of light-sensitive cells. Rods and cones. Thank you, Andrew. Right, so you've got about 120 million rod cells. Those rod cells provide you with your vision in dim conditions. And then there are about 7 million cone cells, and they give you your colour vision in good light at least. So altogether then, those 127 million cells roughly are connected to a nerve fibre layer, which is just about visible in this young patient. You can see some silvery, watery looking reflections which radiate round like this towards the optic nerve head. Okay, that's the end of the optic nerve, at which point there are 1.2 million nerve fibres which take the picture information off towards your brain. You can also see in this picture, labelled with an arrow there, is the macula. Who's heard of the macula, or age-related macular degeneration possibly? Okay, so the macula is where you've got the most dense arrangement of cone cells, photoreceptors or light-sensitive cells, and that gives you your detailed central vision. And macular degeneration, which typically affects people in their late 70s and 80s, affects that area. Age-related wear and tear means that people lose that fine central vision. And also in this picture you can see these red lines, some paler, some darker. Those are the arterioles and venules, or small arteries and veins, which take blood in and out of the forwardmost layers of the retina. Okay, I think that's everything covered on that slide. This is a sketch, a drawing I made during my university training while looking down a microscope at a cross-section of some human retinal tissue, so a bit of human retina. Okay, and you can see under the microscope then that the retina looks highly organised. It's got 10 or 11 layers depending on how you count them. In this picture, light would arrive on the retina at the top of this slide. Okay, so the uppermost layers in this picture are the forwardmost layers in your retina, nearest the centre of your eye. Light passes through the first layers, through these various nerve cells, and is absorbed in this layer here, in the photoreceptor layer, where the rod and cone cell end segments are. Okay. Now, underneath the photoreceptors is something called the retinal pigment epithelium, or the RPE. And that's a layer of pigment cells, dense pigment, which works to absorb any stray light. And more than that, it's involved in maintaining the rod and cone cells, the photoreceptors, in the most remarkable way that we'll talk about later. At the bottom of this slide, there's a layer called the choroid. I've only just shown a very small amount of the choroid, but that gives the retina its very rich blood supply. It really needs that blood supply in order to keep functioning. And the retinal pigment epithelium, the RPE, is involved in transporting nutrients to the rod and cone cells and getting rid of their waste products. So to think of the retina merely as a fine coating, an even coating of light-sensitive cells, a bit like the film in a camera might be, is very much an oversimplification. It's actually composed of about 4 layers of neural cells at least, and they're intricately woven together, connected together. This slide here from a textbook doesn't really do things justice, but it shows how those cells might be wired together. They're actually wired in such a way that the eye does some preliminary processing of the image before it ever reaches your brain. So the way those cells are connected together works to give you edge perception. So when you look at an edge that's got some contrast, like for example an open window, you see there's a sharp line, a demarcation between the light that's flooding in through the window and the shadow on the wall beside it. Your eye has already started to process that information in order to enable you to detect that edge. And it's also wired in such a way that you get your colour perception as well, so that you can tell the difference between different colours. And that's done in part before the information reaches your brain. So, very quickly, moving on, we've had a whistle-stop tour of the globe, or the eyeball. A little bit more detail on the retina at the back itself. I want to draw your attention briefly to some of the structures around the eye. This drawing shows the 6 muscles around the eyeball, which work to move the eye around in its socket, or orbit, to give it its proper name. 2 muscles, these at the left and the right, they are like yoke muscles, which move the eye left and right. The remaining 4 muscles work to give the eye upwards and downwards movement, and they also contribute to the horizontal movements and rotational movements of the eye as well. Of course, you have 2 eyes as well working together. Here's another picture showing the eye and the muscles around it, the extraocular muscles within the orbit. You can imagine how those muscles could pull the eye into any required position of gaze. And in order to move your eyes around so that you can see the world you need to see in all its aspects, those 6 muscles for each eye have the richest blood supply of any muscle in your body other than your heart itself. So you might think your arms and your legs are busy keeping you upright and balanced, but actually your eye muscles, or the extraocular muscles, need a richer blood supply in order to keep your eyes well coordinated. Such is the scale of their energy requirements. So this slide shows what's known as an ocular motility test. Here a person has been asked to follow maybe a torch up and to the left and up and to the right, and into these other 9 positions in order to assess whether their eye movements are properly coordinated. And you can imagine just how well coordinated those movements need to be in order for the brain to get one picture and not to see 2 different images of the world. That's what's known as single vision, or binocular single vision. Now, actually, the visual system will tolerate a small misalignment of the eyes. You can demonstrate that by just touching gently on one of your lower eyelids and nudging the eyeball upwards on one side. And you'll see that very quickly you will get double vision if you move one of the eyes even a small amount. Right, okay. So here's a quotation from Isaac Newton. He asked, "Was the eye contrived without skill in optics, and the ear without knowledge of sound?" And about 100 years after these words of Newton, William Paley, who was a philosopher, a Christian philosopher, wrote in his book Natural Theology that just as the complexity of a watch, if you were to find one on the street, that might force you to believe that it had an intelligent designer, a watchmaker, so the complexity of living creatures around us must be evidence that there is a designer or a divine creator. We've already said many, however, now argue against this idea, and among them is Charles Darwin, very famous, and more recently, man Richard Dawkins, much publicised, and he argues that the eye evolved without the intervention of a creator, without any intervention from a creator. And he wrote a book called The Blind Watchmaker in 1986. Okay, so Charles Darwin, famous for having written a work on the origin of species, and so opening the debate about evolution. What did he actually say? Well, he said, "To suppose that the eye, with all its inimitable contrivances for adjusting the focus to different distances," we've already seen that with the crystalline lens and the ciliary muscle, "for admitting different amounts of light, as the iris does through the pupil, for the correction of spherical and chromatic aberration," that just means that it's optically very good because of its shape, to suppose that all that could have been formed by natural selection and evolution seems, I freely confess, absurd in the highest possible degree, which all good so far. But then he went on to say, "Yet reason tells me that if numerous gradations from a perfect and complex eye to one very imperfect and simple, each grade being useful to its possessor, if that can be shown to exist, if further the eye does vary ever so slightly and the variations be inherited, which is certainly the case, and if any variation or modification in the organ be ever useful to an animal under the changing conditions of life, then the difficulty of believing that a perfect and complex eye could be formed by natural selection, though insuperable by our imagination, can hardly be considered real." So, very long sentence, but what Darwin was saying, I think, was, yes, the eye is a remarkable and wonderful thing, but he still felt that the eye could have evolved. Okay, so evolution, we hear, operates through the survival of the fittest, and thereby what's known as natural selection of those organisms which deserve to survive in any environment, and possibly also gene mutation which changes organisms over time. Okay, I don't know what you all think about evolution, but it's I think important to have an understanding of what the evolutionists are actually saying. So we'll have a brief overview of how evolutionary theory proposes that the complex eyes of mammals like you and me may have evolved. Almost all animals and some plants respond to light in some way, and so it's proposed that the eye evolved bit by bit from very simple origins, from single-celled creatures, in fact, to more complex ones. Now, it's said that any kind of visual sensitivity would provide some sort of advantage, adaptive advantage for an organism in changing environments. Here are two of the simplest light-sensitive creatures on the planet. Amoeba proteus and paramecium are examples of single-celled organisms which exhibit a property called photokinesis. What that means is there is a change in the rate of movement in the presence of light. So amoeba, like this one on the left, move around less in the presence of light than they do in darkness. Paramecium conversely moves around more in the presence of light than it would do in darkness. Slightly more complicated than that, but a single-celled creature nonetheless. Euglena viridis here has a flagellum, which is sort of like a propeller in order to move the creature around. And beside that, it has a light-sensitive area. And on the opposite side, it has a dark spot, a pigment spot, which shields the light sensitive area from any light which would enter from this side. Okay, and this thing exhibits a property called phototaxis, which means that it can orient itself or move in response to light in some way. Now, evolutionists would say then that these organisms are evolving step by step from the really simple to the slightly more complicated and onwards. So the next step would be creatures with more than one cell. And on the left there is Lumbricus terrestris, a type of earthworm. It has a few single light-sensitive cells scattered at the base of its skin. And then evolutionary theory would have it that the next stage in the development of the eye was to group those cells together in order to increase the sensitivity to light somehow, thus enabling the organism to respond to dimmer lights, shall we say. An example of that being the aquatic annelid worm on the right. The eye could be improved next if you were to arrange those cells in a depression or a cup shape like this, okay? This is the eye that you would find in the common limpet at the seaside. Okay, and by doing that sort of arrangement, you give the creature some sort of direction sense. Light coming from this side will be absorbed by these light-sensitive cells, and light coming from the other side will be absorbed by these. So there is some sense in which direction the light has come from. And the optics of that eye would be improved considerably if you enclosed the eye almost completely, only allowing a very small opening at the entrance, a pinhole pupil. That eye would work a bit like a pinhole camera, if you've come across those at all. A pinhole camera doesn't need any lenses. The image is well focused on the back of the film because there is only a very, very small opening at the front. And an example of that sort of eye is found in a mollusk like Nautilus down here. Okay. Slightly better improved again would be if you were to grow a thin transparent skin or cuticle across the pinhole opening, as is found in the eye of the edible snail, and that would prevent debris blocking the pinhole opening or getting into the eye and causing it damage. The eye of the edible snail also has some pigment cells scattered amongst the light sensitive one. They work in order to absorb stray light and to give the image better clarity. Okay, just one more slide on this subject now, moving on pretty quickly. Evolutionists would say that the next stage of development from the snail's eye would be for the skin over the front of the pupil to thicken slightly in order to make a lens, in order to focus the image better. They would claim that that if a second layer of skin would grow over from the retinal cells and thicken, you could have a second lens like there is in the human eye in order to focus the eye for different distances possibly, and so on and so forth. Part of the cuticle could grow across and become pigmented to form a kind of a barrier like we have with our iris and a pupil at the centre. And so on and so forth. Evolutionary theory has it that the complex eye found in mammals like you and me is related by evolution to the eyes of invertebrates like the squid. So that's enough of that for now. So how many of you heard this term intelligent design? Yeah, so there are a few nods around the room. So just as William Paley, we've already talked about, and others like him, put forward an argument for a creator based on apparent design in creatures and in the laws of the universe, in fact, so supporters of this theory, intelligent design, are saying much the same thing, that the complexity of living things points to an intelligent designer. Now remember, we've said evolution by natural selection requires stepwise changes in an organism's structure over very long periods of time, each of those changes providing some kind of advantage. Now, especially important then in intelligent design, if you like, the counter-argument, is the idea that some things are just irreducibly complex. So, in other words, some things could not be made any simpler and still work, or they couldn't be made any simpler and still provide any advantage at all for the organism. Or worse still, if you were to change something partially, a stepwise change might actually render the creature handicapped in the race for survival of the fittest. So thinking about that then, irreducible complexity in relation to the eye. Well, the eye has so many parts that are so special and unique, but one of the most notable is the iris, the coloured part of the eye, which controls the shape and size of the pupil at its centre. So this is someone's iris in all its detail, blown up really big, as I might see it at the microscope at work. Now, in order to change the size of the pupil at its centre, the iris has two very different muscle configurations. There is a sphincter muscle, which goes all the way around the margin of the pupil, all the way around like this, like a purse string. And when that muscle pulls tight, it works just like a purse string in order to pull the opening of the purse closed. Okay. The second muscle configuration is what's known as the dilator muscle, and that works radially, like spokes on a bicycle wheel, in order to pull the opening of the pupil in dimmer conditions, in darkness. And actually the dilator muscle, for anyone with any interest in biology, I don't know whether that's many of you, but the dilator muscle is a really peculiar hybrid of two tissue types. It's a mixture of epithelial and muscle tissue, which I think is pretty unique. So these muscles are very different, these two muscles. And for the iris to work properly, both of those muscles need to be there. On its own, either one of them would be of no use at all. And we can demonstrate that quite simply. In this picture, I've had a drop of tropicamide instilled into my right eye. Tropicamide is a drug which is related to the belladonna family. It works by preventing nerve impulses acting on the sphincter muscle, or the purse string muscle of the iris. So you can see what happens. With the sphincter muscle disabled, the dilator muscle pulls the pupil wide open. So one of those muscles on its own is pretty much useless. So it strikes me, therefore, that if we accept that the iris evolved by the chance events of evolution, we must believe that both those features, both the sphincter pupillae and the dilator pupillae, those two muscles, must have developed together in unison or about the same time. And that might demand a very large, or perhaps incredible, developmental leap. Okay. Two other parts of the eye which are also very special and unique are the cornea and the lens, and they are special in part because they are transparent. Not that many structures in the body are. The cornea, in fact, the clear window at the front of the eye, is transparent despite being made of exactly the same material, collagen fibres, as the white of your eye, the sclera. Okay, and what makes it transparent is that those fibres are arranged in a very regular arrangement, and the quantity of water, the hydration of the cornea, is maintained at a very precise level in order for it not to become cloudy. And it needs a good blood supply to do that, you would think, but despite those high energy requirements, actually it doesn't have any blood vessels, and thus it's transparent. Now, because the cornea is transparent and doesn't have any blood vessels in it, it has to get its blood supply from the limbus, where there is a ring of blood vessels around the edge of the cornea, and most of its oxygen, in fact, comes from your tear film while your eyes are open anyway. Okay, and if the cornea is infiltrated with blood vessels, as would happen if it was scarred after a corneal injury, well, what we're left with is seriously impaired vision. So it has to be without blood vessels in order to be transparent. The lens behind it is also transparent, in part because it has no blood vessels in it. It's avascular. Now, growing these structures poses a problem. Growing a lens inside the eye without blood vessels, it has to be nourished somehow, and so these pictures show what happens in the womb. Pictures 1 and 2 on the left show how in the womb there is something called the hyaloid system, a group of arteries which connect the developing lens at the front of the eye to the optic nerve head at the back of the eye, in order to feed it and nourish it while it grows. And the pictures on the right, pictures 3 and 4, show what happens later. The hyaloid artery degenerates and disappears about 6 weeks before the child is born, and in its place there's a clear canal which fills with liquid. So if we accept that the eye evolved by chance, we also have to accept that the mechanisms by which the eye grows in the womb, in utero, we have to accept that those must also have evolved by chance at the same time. And also the mechanism for the disintegration of those blood vessels, so that they're gone by the time the child is developing its vision. That must also have evolved at the same time, which seems very remarkable or unlikely. Okay, here's another question. The iris and the lens are two places where I see what I think is irreducible complexity. Here's another example that's not my own. We might ask, how did the first cell become light sensitive? And this is what Charles Darwin wrote on The Origin of Species. He said, how a nerve comes to be sensitive to light hardly concerns us more than how life itself first originated, which is a very bold statement. I may remark that several facts make me suspect that any sensitive nerve may be rendered sensitive to light, and so on. Okay, so really he didn't answer the question of how the first light-sensitive cell came to be. And the reason is, it was completely beyond the science of his day in the 19th century. No one understood at that time what happens when a photon, a particle of light, hits a light-sensitive cell in the retina. And I don't want to send you all to sleep with any more detail than is necessary. It's too complicated to go into much detail here, but I hope it suffices to say that the process by which light is transferred or transduced from a nerve into a nerve impulse allowing you to see, that's very complicated indeed. Each photoreceptor cell, each rod cell at least, contains a pigment called rhodopsin, and that pigment is caused to change shape when a light particle hits it, and that change in shape starts a complex series of reactions, chemical reactions, a cascade of them, at least 5 steps to my mind, and the chemical reactions result in the build-up of electrical charge at the edge of the nerve cell, the rod cell, which then travels down the network of nerve cells to your brain. And there's a second similarly complex series of reactions which returns the system to its starting point so that you can see continuously, so that you don't run out of rhodopsin, so that there is enough pigment for you to see for more than just an instant. If you want to read up a bit more about this, you could either have a look at a book called Darwin's Black Box, which was written by Michael Behe, an American biochemistry biochemist, and he argues from many different aspects of biology or biochemistry that certain things are irreducibly complex at a cellular level, okay, right at the most basic level of life, if you like. Or if you want to see a little bit simpler illustration, or if you're just interested in proving what I've tried to tell you today, you could have a look at this website. Or there was a series of booklets here produced by the Christadelphians in Sheffield. It was Lawrence Cave, who's now at Coventry, who was involved in producing this series of booklets, and there is one on the eye called Your Remarkable Eyes, and it's just focused on this process, really, on showing that this chemical process in your light-sensitive cells is irreducibly complex. So if you want a bit more information or to prove it for yourself, have a look at that website or write to Lawrence Cave at Coventry. I'm sure he would send you this information. So that's what happens in your rod cells, and I think that the majority of those steps would still be required in a single-celled organism. Okay, so enough of irreducible complexity. Have a look at the details there. I think it's irreducibly complex. What about this question then? Some critics of intelligent design have sought to show that what we might propose as being irreducibly complex is not actually irreducibly so. But it's more often that you find alternative arguments. Some others have pointed to apparent flaws in the anatomy or physiology of living things, things that they might say, that's bad design, that's not well designed, and therefore they suggest that organisms must have developed by chance rather than intelligence. And so here we go then. Here is possibly the most common criticism of your eye's design and mine. Okay, is your eye wired back to front? You remember when we were looking at eye evolution theory, all the examples we considered were invertebrates, creatures without a spine, and we finished with the squid eye, which looks diagrammatically and optically very similar to your eye and mine. It's similar to the eyes of mammals or vertebrates, but there's a noticeable difference. In the invertebrate eye, you have the light-sensitive cells arranged in a depression or a cup or an eyeball. And in this hasty illustration, those are the light-sensitive cells that I've drawn there. And the nerve fibres then run backwards towards the animal's brain from the light-sensitive cells, taking the picture directly with them. Okay. Whereas in the eyes of vertebrates, mammals and humans, it's a little bit different. The light-sensitive cells, yes, they're arranged in a pit or depression like this in the eyeball. But the nerve fibres, instead of running directly backwards to the brain, they actually course over the top, if you like, over the top of the light-sensitive cells before leaving through an aperture in the back of the eyeball as an optic nerve. Okay. So what that means then is that when light enters the eye, it has to course through all these other structures, these nerve fibres and whatever other blood vessels might be with them, before it reaches the light-sensitive cells. And thus, these eyes are sometimes called inverted. The eyes of vertebrates are called inverted. Okay. And that's because the light-sensitive cells, if you like, face away from the light, or they're buried under some other structures. And this gives rise to something called the blind spot. How many of you have heard of the blind spot? Okay. Different from the one that you have over your shoulder when you're driving. Okay. At the head of the optic nerve here, the nerve cells, the retinal ganglion nerve cells, are packed in so densely that there's no room for any light-sensitive cells. There can be no rods or cones at that point. So each retina, your right and your left eye, has a small area that is non-seeing. And you can demonstrate this for yourself. There's a number of ways of doing this. I'll just show you one. It may or may not work, and it'll be a good proof as to whether you're awake or not. If you hold out both your arms like this, so that you're looking at your two thumbs held outwards like this at arm's length, and you look intently at your right thumbnail and close your right eye. So you're looking at your right thumbnail with your right eye closed. Now if you separate your thumbs so that you're pulling your left thumb maybe half a foot, 15 centimetres to the left, while still looking at your right thumbnail, there will be a point where your left thumbnail disappears. Okay? Have any of you found it?
Yes.
One or two? Good, that's great. The rest of you can practice later at home where you feel less silly. Okay, or I'll show you later, or try to. Okay, so you've seen that there's a blind spot, and Richard Dawkins, we've already mentioned, he says that this blind spot is evidence of untidy wiring which would embarrass any engineer. And so evolutionists like him say that this arrangement must be the result of chance evolution, in which errors in design, so to speak, were incorporated through successive alterations in order to make the eye work in a functional manner. So, in other words, the eye made a mistake while it was evolving, but never mind, there was a workaround, there was another way around things. Okay, so how do we respond to that? Well, here's a recap of the retinal layers. Light enters at the front, makes its way through all these structures, through the nerve fibre layers, that complex arrangement of nerves, before it reaches the rod and cone cell end segments in this layer, and any stray light is absorbed in the retinal pigment epithelium. And behind that layer of dense pigment, retinal pigment epithelium, there is the choroid, which gives the retina, in fact, most of its blood supply, the extremely rich blood supply that it needs. So here, diagrammatically, is a rod cell on the left and a cone cell. And you can see at the bottom there are the rhodopsin pigment discs, which contain that pigment which is sensitive to light, or in a cone cell it's something called iodopsins. And those cells have their end segments nestled between villi or fingers of the retinal pigment epithelium. That's a retinal pigment epithelium cell there with all its fingers, and the rod cells nestled within those. Okay, now, and there are these dark spots here. They're melanin pigment granules, which are there to absorb stray light and to improve the quality of the vision. So you might say there's no better place to put the retinal pigment epithelium. If you want that density of pigment, there's no better place to put it than at the back of the eye and to have the photoreceptors where they are. But more than that, the damage which is caused by light on these rhodopsin pigment discs, whenever you are exposed to light, which is most of the time while we're seeing, okay, the damage which the light does requires that these rhodopsin pigment discs are actually replaced and recycled continuously. And so they are nestled in the retinal pigment epithelium for that purpose. Okay, there is about a 2-week cycle during which all your rhodopsin pigment is completely recycled. And in order to do that, the retinal pigment epithelium actually breaks off chunks of spent rhodopsin discs and digests them and puts those waste products back into your blood supply and feeds your rod and cone cells with all the nutrients needed to manufacture more rhodopsin or iodopsin pigment discs. And in order to do that, the photoreceptors need an extremely rich blood supply in order to do it, and thus they are placed nearest the choroid, that layer of dense blood capillaries which give them that rich blood supply. In fact, the choriocapillaris, that's the finest layer of capillaries right at the front of the choroid, right behind the RPE and your photoreceptor cells, that tissue has the largest blood flow per gram of any tissue in your body. Okay, such is the requirements of oxygen and nutrients enabling you to see continuously with the resolution with which you see. And thus there is no way I can see of constructing an eye like that without having the nerve fibre layer out of the way, furthest away from the blood supply, nearest the incoming light as it happens, and the light sensitive cells, well, further away, but it doesn't actually cause much attenuation of the light, and more recently scientists have found that other nerve cell structures called Muller cells, which run vertically through all this arrangement, actually act or may act like pipes in order to funnel the light downwards through all these other nerve fibre layers towards the light sensitive cells where it's really needed. And yes, it gives rise to a blind spot, but how many of you knew you had a blind spot? Probably none of you, unless it was demonstrated to you by a school teacher or some other scientist or optician. Okay, because we have two eyes and the blind spots are not overlapping, so one eye makes up for the other, and in the few circumstances where one blind spot does come into play, the brain is extremely good at making up the detail. As you've seen, you know, when you did this with your thumbnails, yes, the thumbnail disappeared. What did you see behind it? Well, whatever was behind it, you know, the brain fills in the picture. One last question then. Okay, another example of eye design criticism, one I've not come across very often, I must admit, but some people say that the eye must demonstrate poor design because so many young people, let's say, are long-sighted or short-sighted and thus need to wear glasses. So we're not talking about what happens with middle age where people have difficulty with close vision and either need to take their glasses off or put a pair on or wear a separate pair for reading. We're talking about young people becoming long or short-sighted. What causes this? Well, simply put, the factors which contribute to whether the eye is properly focused are mainly the curvature of the cornea at the front of the eye, less so the curvature of the lens behind it, and secondly, the length of the eyeball from front to back. Okay, so most short-sighted people are so because their eyeball has grown too long in their youth. So this is my eye here. When I was about 18 or 19, it started to lengthen from back to front, and so the light which was properly focused on the retina at the back, actually it's focused somewhere in front of the retina, and by the time the light hits the retina it's gone blurry and out of focus again. And likewise, people who are long-sighted, well, their eyeballs are too short, so light would be focused somewhere behind the eyeball if the retina didn't get in the way. Okay, so how do we respond to that question? Well, corneal curvatures and eyeball lengths have something called a normal distribution or an approximately normal distribution, but no one's ever talked about this in a lecture here before. Okay, if you were to group people according to the curvature of their corneas or the length of their eyeballs, okay, so these people here have very flat corneas, and these people here have very steep corneas, and a typical person has a cornea with a radius of about 8 millimeters. Okay. Likewise, these people here have short eyes, these people here have long eyes. A typical person has an eye that's about 22 millimeters long. But the important thing is that there is actually considerable variation. There are quite a few people with steep corneas, flat corneas, long eyes and short eyes. Okay, if you were to combine corneas and eyeballs at random, you would expect a similar distribution of spectacle prescriptions. Okay, you would expect that there'd be quite a lot of very long-sighted people and quite a lot of very short-sighted people. Obviously, the average would be to be neither long nor short-sighted, but there would be a lot of high spectacle prescriptions. But that's not what you find. Actually, the graph looks like this. And there is a massive spike in the middle where most people don't require glasses for relaxed, clear distance vision. And very, very few people, really, have high spectacle prescriptions at either end for long sight or short sight. And this is absolutely fascinating, and there's been a lot of research, and really people are only just starting to hit upon what it is that makes this the case over the last 15 years probably. So there's this remarkable process called emmetropization, which means that in most people the eyeball and the cornea, well, the eyeball, let's say, grows to the correct length so that the eye is properly focused. And the mechanism by which that occurs is still not fully understood. It's probably the hottest topic right now in vision science. It has to do with genetic and environmental factors, but also on how well light is focused on the peripheral retina. Has an effect on making the eye grow. Okay, so there we go, we're nearly at the end. What do you think? Could all this have happened by chance? Newton, Paley and others concluded that the laws of the universe, the complexity of living things, must point to a creator. Darwin and those after him saw an alternative explanation in evolution by gene mutation and natural selection, and they proposed the evolution of the eye from simple origins. And over the last 20 years at least, there's been this rebrand of creationism, if you like, as intelligent design, citing irreducible complexity as proof that life can't be here by chance, that there must be a designer. In response to this argument, some have ventured to say that the eye actually presents features that are bad design. I don't agree. But the argument is so loaded with emotion that it's never going to be easily settled. And if you look at some of the literature on this subject, you'll see that it's not altogether grown up, that people really have an interest in maintaining their position and will argue in a rather childish way, to my mind anyway. And we can understand that. If you've always believed in God and you have your hope in your God, then it's not nice to be told, well, you're just silly, there's no God, of course, or vice versa. If you've always believed that things are here by chance and someone tries to prove that there is a creator, well, if there is, you're going to be responsible to him. So that's not easily palliated either. So we're in a place of worship. Let's just quickly see what the Christian and Jewish Bible's position is on the matter. So from Proverbs 20 verse 12 we read, "The hearing ear and the seeing eye, the Lord has made them both." And I wonder whether Isaac Newton had those words in mind when he said much the same thing. Or from Ecclesiastes 11 verse 5, "As you do not know the way the spirit comes to the bones in the womb of a woman with child, so you do not know the work of God who makes everything." And this one, which Andrew referred to in his opening prayer, Psalm 139, David is filled with wonder by the knowledge of God, which he says is too wonderful for him. He says, "For you formed my inward parts, you knitted me together in my mother's womb." I love this rendering actually, the English Standard Version's great here. "I praise you, for I am fearfully and wonderfully made. Wonderful are your works, my soul knows it very well. My frame was not hidden from you when I was being made in secret, intricately woven in the depths of the earth. Your eyes saw my unformed substance. In your book were written, every one of them, the days that were formed for me, when as yet there was none of them. He says to God, you knit me together in the womb, that he was intricately woven. Isn't that wonderful?